Now that we've learned a couple basic derivative rules, I want us to look at some different examples for how we can apply those rules. In this first example, we have a particle that moves along the x-axis. According to the position function, x of t is equal to t cubed minus 2t squared plus 4. Now I could ask a lot of different questions about this position function. One possible question might be, find the average velocity on the interval 1 less than or equal to t less than or equal to 3. Average velocity. Now when we see those terms, whenever you see average velocity, I hope the first thing that we would think is average rate of change, especially since the function that I'm given here is a position function. When I find velocity of position, that's rate of change. And so what I'm looking for here is the average rate of change. And so when we see average rate of change, we should always think of the formula f of b minus f of a over b minus a. In this case, my function is x of t, so I'm going to do x of 3 minus x of 1, because 1 and 3, that's my a and b, over 3 minus 1. And then to find this value, we're just going to get these numbers by plugging in 3 and 1 into our position function. If I plug in 3, then I get 3 cubed minus 2 times 3 squared plus 4 minus, and then I'm going to plug in the 1. 1 cubed minus 2 times 1 squared plus 4 over 3 minus 1, which is 2. And let's see, what do we get? 3 cubed is 27 minus 18. That would be 9 plus 4 is 13. Minus, and then when I plug in 1, I get 1 minus 2, which is negative 1, plus 4 would be 3 over 2. And so 13 minus 3 would be 10 over 2, or just 5. And so 5 would be my average velocity for t between 1 and 3. Now instead of being asked for average velocity, I could be asked for instantaneous velocity. So let me erase my work here. And let's say that I'm asked for instantaneous velocity whenever x is equal to, or for time, not x, sorry, for time t equal to 2. Well, we have a note card that reminds us that instantaneous rate of change simply means derivative. And so instantaneous velocity, that's the same as instantaneous rate of change, which means what I'm looking for here is the derivative of this position function at t equals 2. Remember that if I take the derivative of position, that's actually equal to velocity. And so I'm going to do a derivative of this position function. That derivative would be 3t squared minus 4t. So that's my velocity function, my derivative function. And I want to know what the velocity is when t equals 2. So velocity at 2 would be 3 times 2 squared minus 4 times 2. And that would be 12 minus 8, or 4. Now another type of question that we might be asked about this same function is, when is the particle at rest? When is the particle at rest? Well, if the particle is at rest, that right there means that Whoops, I don't know what just happened there. That means that our velocity is going to be equal to 0. At rest means velocity equals 0. And so, again, I need that velocity function, which I've erased. So let me find it again really quickly. The derivative of position is velocity, and that derivative would be 3t squared minus 4t. So if I want to know when this particle is at rest, I'm going to take my velocity function and I'm going to set it equal to 0. And then I need to solve for time. Well, I see that I have a quadratic here, and anytime we have a quadratic, we should know that in order to solve it, we need to factor. So I look at this, and I can factor out a t, and when I do that, I'm left with 3t minus 4 equal to 0. So now that I'm factored, I know that t equals 0, or 3t minus 4 equals 0, and t would be equal to 4/3. And so that means that my particle is at rest whenever t equals 0, or when t equals 4/3. All right, let's move on and look at a different type of question. Here I have the question, is the following function increasing or decreasing at x equals 8? And then we have a function y equals the cube root of x squared minus x squared plus 5x. Well, the first thing I would want you to do on a question like this is to annotate for increasing and for decreasing. We have learned that if a function is increasing, that means that its derivative, f prime, should be greater than 0. This is from that chart in Unit 3. And likewise, if a function is decreasing, then that means that f prime would be less than 0. Or I could have written dy dx. In this case, my function is defined by y. So what I'm really looking for is my derivative positive, greater than 0, or is it negative, less than 0, whenever x is 8? Well, hopefully it's obvious that what we need to do here is find a derivative. So let's do that. Now I notice that I have a radical, and whenever I have a radical, I need to rewrite that as an exponent. So instead of the cube root of x squared, I'm going to rewrite that as x to the 2/3 power, minus x squared plus 5x. Now we're ready to find a derivative. dy dx is equal to 2/3 x, that exponent comes to the front, and then I need to do 2/3 minus 1, which is 2/3 minus 3/3, which would be negative 1/3. The derivative of negative x squared would be negative 2x, and the derivative of 5x is just 5. Now if I've got to substitute back in a number, which I do, notice here I want to know if this is increasing or decreasing whenever x equals 8. So I need to plug in 8 to my derivative and find out if the derivative is positive or negative. That will tell me if the function is increasing or decreasing. But before I plug the function in, I'm going to rewrite this back into a form that doesn't have the negative exponent. So I'm going to have 2 over 3. My exponent is negative, so that means that I'm going to write x in the denominator. The exponent is 1/3, and so I'm going to rewrite that as the cube root of x. And then the rest of my derivative function will stay the same. Now if I want to know the derivative at 8, the way that we denote that with this notation is with a little bar like this, derivative at x equals 8, and then I'm just going to plug in 8 for all my x's. So I've got 2 over 3 times the cube root of 8 minus 2 times 8 plus 5. So that equals 2 over 3 times 2, the cube root of 8 is 2, minus 16 plus 5. And we could simplify that more. However, remember that the only question here is the derivative at x equals 8 positive or negative? Well, obviously, since that 16 is negative, this whole value is going to be negative. So I know that this is going to be less than 0. And that means that, therefore, the function is decreasing. All right, let's look at one last example. In this question, we want to know on what intervals is the following function decreasing and concave up. So now I've got two questions here to consider, two different features of the graph that I want to think about. And so I want us to stop and take a moment to annotate. First of all, what does it mean if a function is decreasing? Well, that means that f prime is less than 0, or f prime is negative. And then, what does it mean if a function is concave up? Well, if you remember, the first derivative of a function tells me if it's increasing or decreasing. Concavity is information I get from the second derivative. And if I want my graph to be concave up, I want the second derivative to be greater than 0. So this is what I'm looking for on this particular function. I'm going to go ahead and start by taking a derivative, and let's answer that decreasing question first. Let's find the intervals where our function is decreasing. So I'm going to find f prime, find the derivative, and it's equal to 12x squared minus 12x. That's my derivative. Now, if I want to find just the intervals where this function is decreasing, the best way to do that is to first of all find the zeros. Because if I find where the derivative is 0, then I consider the intervals in between the zeros and find out if the function is positive or if it's negative. Because if I'm changing from positive to negative, I have to cross a 0. And on either side of the zeros, I should be either positive or negative. So I'm going to start out by setting this equal to 0, and I'm going to solve for x. Now again, I have a quadratic, and so that means if I'm going to solve, I have to factor. I'm going to factor out a 12x, and if I do that, I'm left with x minus 1. And if I set each of these equal to 0, then 12x equals 0 and x equals 0, or x minus 1 equals 0 and x equals 1. So now I know that my derivative is equal to 0 at 0 and at 1. So at this point, what I'm going to do is draw a little number line, and I'm going to mark off 0 and I'm going to mark off 1. If those are the only places that my derivative equals 0, then on either side of these numbers, my derivative should either be positive or negative. So to start out, I'm going to look at this interval less than 0, this interval right here, and I'm going to pick a number in that interval, like -2. -2 would be a number that's less than 0. If I plug in -2 to my derivative, and when I plug it in, I'm going to go back to the factored form, because that tends to be the easiest place to plug things back in. I'm going to plug in -2, and the only question that I need answered is my derivative going to be positive or negative when I plug in -2? Well, if I put -2 right here, that's going to give me a negative, and if I plug in -2 in here, that also gives me a negative number. And so I'm multiplying a negative times a negative, and that means that when I plug in -2, I should get a positive result. Now let's pick a number that's between 0 and 1. For instance, 1/2. If I plug in 1/2 here into the 12x, that's going to give me a positive value. However, if I plug 1/2 in here to x minus 1, that's going to give me a negative value. And so a positive times a negative would result in a negative. Finally, I'm going to pick a number bigger than 1, like 2. If I plug positive 2 into the 12x, I get a positive value. And if I plug positive 2 into the x minus 1, I get a positive value again. And a positive times a positive is a positive. So that means that my function is decreasing. Remember, we're interested in where this function is decreasing. That only happens right here between 0 and 1. So we're decreasing for 0 less than x less than 1. Now we need to answer the other question about where this function is concave up. Now concave up, remember, that's a question about that can be answered with the second derivative. But in order to answer that question, I need to find the second derivative. And the way that I'm going to do that is just by taking a derivative of the first derivative. My first derivative was 12x squared minus 12x. The derivative of that function would be 24x minus 12. So that would be my second derivative, because now I've taken two derivatives from my original function. Now again, if I'm looking for intervals of concave up or concave down, the first thing I want to do is find the zeros. So I'm going to set this equal to 0, and I need to solve for x. Well, if 24x minus 12 equals 0, then 24x equals 12, and x equals 12 over 24, or 1/2. So x equal to 1/2, that's my only 0 for the second derivative. Now again, I'm going to do a little number line, and I'm going to put 1/2 on there. So this is a potential inflection point on the graph of my function, but we need to make sure that the sign actually changes. So I'm going to pick a number in this interval less than 1/2, like 0. I always like to use 0 whenever I can. And if I plug in 0 into my second derivative, I'm going to plug it in right here. If I plug in 0 for x, then I end up with 0 minus 12, which is a negative value. So that interval, on that interval, the second derivative is negative. Then if I pick a number bigger than 1/2, like 2, and I plug that number in for x, then I get 24 times 2 minus 12, which will result in a positive value. And so my function is concave down up before 1/2, and then it's concave up after 1/2. Now my original question was interested in where the function is concave up. And so I can see here that my function is concave up on this interval for x greater than 1/2. Now really what I want to know here, if we go back and look at our original question, it wants to know on what interval or intervals is the following function both decreasing and concave up. Well, I'm only decreasing between 0 and 1, for x between 0 and 1, and I'm concave up for x greater than 1/2. And so the place where those two intervals overlap would be for 1/2 less than x less than 1. That would be the interval where my function is both decreasing and concave up. I have a feeling I need to explain that again. Let me do another number line here. So 0, 1/2, and 1. Those were my critical numbers in this function, my possible maximums or minimums, places where my derivatives are equal to 0. And I found out that my function was decreasing for x between 0 and 1. So that would be this interval right here, 0 to 1. I also found out that my function is concave up for all x's that are greater than 1/2. So that's all of this interval right here and on going to positive infinity. The place where those two things overlap is right here from 1/2 to 1 for x between 1/2 and 1. And so that interval would answer our question.